Alright, what's up? In this video we are going to look at calculating limits using limit laws. Now in the video before this one in the playlist, we looked at limits and we used tables and graphs. But now we're going to learn how to calculate limits without using tables. And as I mentioned in the previous video, you don't use tables to find the limit of a function. So the limit laws, we've got suppose that c is a constant and the limits, these two limits here, the limit of f of x and g of x as x goes to a exist, then the limit of f of x plus g of x and the limit of f of x minus g of x as x goes to a is the limit of f of x plus the limit of g of x. And then down here, the limit of f of x minus the limit of g of x. So what this is saying is that if you have multiple terms and you're taking the limit of all those, you can split them up. You can take the limit of each term. And then this number 3 here, that's the limit of c times f of x is equal to the limit of c. It is equal to c times the limit of f of x. So this is saying this c is a constant, so you can take the limit of the function f and then multiply it times c. And then the multiplication and division, you can do them separate and then multiply them together or divide them together. Well, and that's saying that the limit of g of x does not equal 0 when you do the division, because you can't have 0 in the denominator down there. Alright, so let's look at this. So here's my attempt at drawing a graph. It says use the limit laws and the graphs of f and g to evaluate the following limits if they exist. Alright, so let's look at this. So let's use those properties up here, and this says that we can write this as the limit as x goes to -2 of f of x plus 5 times the limit as x goes to -2 of g of x. All right, so all I did is just split them up, and then remember this constant here, I can bring it outside the limit. And so then we just look for the limit of f of x as x goes to -2. So here's x equal -2, and if you remember from the previous video, the limit from the left and the limit from the right have to be the same in order for this limit to exist. So if I come in from the left, you can see as I come in to the left, from the left to -2, my y value is up here at 1. And as I come in from the right, my y value is up here at 1. And so this limit here, the limit of f of x as x goes to -2, is 1. And then that's going to be plus, and now I've got to do the limit of g of x as x goes to -2. Oh, and I'm sorry, I did not label those graphs. The red graph is f and the blue graph is g. Okay. All right. So let's continue. So the limit of g of x as x goes to -2. So I'm coming here to -2, and you can see we're right here, and this is a y value of -1. So that's going to be plus 5 times, and then this limit is -1. And so this is going to give us an answer of -4. All right, so what about the next one? Well, this is equal to the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x. All right. So let's find the limit of f of x as x goes to 1. So as x goes to 1, this limit, this y value here for f is 2. and so that's equal to 2 times, and then g of 1, well, I'm sorry, the limit of g of x as x goes to 1. So as I'm coming into 1 from the left-hand side, we're down here at negative 2. The negative 2 here. As I come in from the right-hand side, we're at negative 1. So you can see the limit from the left and the right does not exist. So this limit here does not exist. And so that means this limit does not exist. All right, because I can't multiply times something that does not exist. All right, and then what about this one? Well, this is the limit of f of x as x goes to 2 over the limit of g of x as x goes to 2. And so what do we get here? Well, the limit of f of x as x goes to 2, we're about, looks like we're about right in here. So we'll call that we're at 1. So that's equal to 1 over, and then the limit of g of x as x goes to 2. So as we go to 2, you can see this limit right here. That's a y value of 0. And so that gives us 1 over 0. Well, we know that's undefined, and in this limit law it says if g of x does not equal 0. So we know this one does not exist. Okay. All right, so that's a little bit of how you can do these limits and stuff. So, you know, looking at a graph, you can split them up like that using these laws right here. And then we've got some more down here. We've got the limit of f of x raised to the n. Well, that's just, we can take the limit and then we can raise it to the power. Okay. Here, the limit of c as x goes to a. This one's just saying that if we're taking the limit of a constant, we just get that constant term back. And then the limit, let's see, these next 3 limits right here. The limit of x, the limit of x to the n, and the limit of the nth root of x, all as x goes to a. Do you see what they're doing? All they're doing, if you've got x to the n, or the nth root of x, all they're doing is taking a and plugging it in for x. Okay, so that's saying that whatever x is going to, you can just replace x with that constant. And of course, in this one and this one, n is a positive integer, n is a positive integer. And for this one, if n is even, then we assume a is positive, because remember that if n is even, that would be like the square root, the fourth root, and we can't take the square root or the fourth root of a negative number. If we do, we get the imaginary numbers. And then this one's similar. We can, this one right here is if we're taking the limit of the nth root of the function, then we can take the limit of the function and then do the nth root of it, okay, where n is a positive number. And if n is even, we assume that this limit right here is positive, because then we would have a negative number under like a square root or a fourth root, and once again we can't do that. All right, so these next 2 examples, they're wanting us to evaluate these limits here, and they're wanting us to use they're wanting us to work these using the limit laws. Okay, so we're going to break this up, and what we're going to do is I'm going to work them out, and it's going to be a lot of steps, and you're not really going to work the problems like this. We've got a property coming up right after this that makes it easier to evaluate these limits, but I think it's good for you to see this, breaking these up, because later on in your calculus class, it's going to be helpful to know how to break these up. It can make the problems easier to do. Okay, so So let's look at this, and then once we see the property after this, after I work these two, we're going to come back up here and work these problems again using that theorem, that property that we're going to go over. All right, so let's break this up. So this is going to be the limit as x goes to 5. Well, let's go ahead and bring the 2 out also. So that's going to be 2 times the limit as x goes to 5 of x squared minus 3 times the limit as x goes to 5 of x plus the limit as x goes to 5 of 4. All right, and you can see all I did is I used those limit laws. Okay, I pulled the constant out. Okay, and then this x squared, well, that's all that is see, I've got a limit law that says that x to the power, x to a power. So I just made it look like those limit laws up there. And so now applying that, that's 2 times, and then remember that property says I can take this 5 and plug it in for x. So that's 5 squared minus 3 times, and then I can plug the 5 in for x, plus, and then the limit of a constant term is just that constant term. All right, and so when I evaluate that, I get 39 as an answer. All right, so same thing on this one. Let's go ahead and split this one up. So the first thing we'll do is we'll write this, the limit as x goes to negative 2 of x cubed plus 2x squared minus 1 over the limit as x goes to negative 2 of 5 minus 3x. All right, so I'm taking the limit of a fraction, so I can split that up. And then what I need to do is I need to split each one of these up. Okay, and I'll do that. So I've got the limit as x goes to negative 2 of x cubed plus, and I'll go ahead and pull the 2 out, limit as x goes to negative 2 of x squared minus the limit as x goes to negative 2 of 1. And that's all over the limit as x goes to negative 2 of 5 minus, and then 3 times the limit as x goes to negative 2 of x. All right, and so that's going to give us, now I can just plug the negative 2 in, so that's negative 2 cubed plus 2 times negative 2 squared minus 1, limit of a constant, that's just that constant term, and then that's going to be 5 minus, and then that's going to be 3 times, and then I plug the negative 2 in for x. All right, and then when I evaluate this, I end up with negative 1 over 11 as my answer. All right, so that's going through and finding the limits, and that is that's showing all the steps. Okay, breaking it up and using those limit laws. But like I said, you're not going to write it out like that. And we have this property here, this direct substitution property. So if f is a polynomial or a rational function and a is in the domain of f, so whatever x is going to, it has to be in the domain of the function, then the limit of f of x as x goes to a is equal to f of a. Well, that's nice right there, isn't it? What is that telling us? If we're taking the limit of a function as x goes to a number, and that number is in the domain of the function, well, to find the limit, we just evaluate the function at that number. Okay, so let's go back up here and look at these problems again. So let's look at this. So according to that property, that is going to give me what? 2 times 5 squared minus 3 times 5 plus 4. That's what it's saying I can do. See, instead of having to go through all of this stuff, I can just evaluate the function at that number. Okay? And so this would give me 39. Okay. Now keep in mind, working this, I'm going from this to this. Okay, you won't do all of this stuff in here. All right, and then the same thing here. Let me just erase this. So according to this property here, well, I can just say this is equal to negative 2 cubed plus 2 times negative 2 squared minus 1 over 5 minus 3 times negative 2, and that would give me negative 1 over 11. So you can see that's much easier. It's a lot quicker, and that's how you're gonna evaluate limits. Okay, that's what you're gonna do. All right. So just remember, whenever they ask you to find a limit, just plug the number in for x. Okay, that's all you got to do. Just evaluate the function at that value. All right, so now let's look at this one. All right, so going by what we just did, and remember, keep in mind that property that a has to be in the domain of f, and obviously we can see it's not in this problem. But let's just plug it in and see what happens. 1 squared minus 1 over 1 minus 1. All right. And that gives us 0 over 0. Now, with you being in calculus, I know that you understand 0 over 0 is not 1. Okay? We know that's not 1. But this is something special, getting 0 over 0. Now, whenever you're finding limits, if you plug that number in and you get 0 over 0, this is what my calculus teacher told me, and I've always remembered this. If you plug it in and you get 0 over 0, do something else. Okay? Do something else. So, some of you may have already had calculus, whether you're taking it for a second or third time, or you may have had it in high school, and you might be thinking L'Hopital's rule. Okay? If you don't know what I'm talking about when I say L'Hopital's rule, don't worry about it. That's later on in a calculus class. But right now, we don't know L'Hopital's rule. That's something we learn later on. Okay? And I'll have a lecture video on that also. So in this one, we got 0 over 0, so let's do something else. So we look at this numerator here, and we can see that we can factor it. All right. So all I did is I factored the numerator. And look at this. You see how these x minus 1s cancel out? That leaves me with the limit as x goes to 1 of x plus 1. Well, now I can just take the 1 and plug it in. So 1 plus 1 is 2. And there's my answer. Okay? So that's what happens when you plug it in, you get 0 over 0. Try something else on it. Okay? So the first thing we've learned, is to factor it. Okay? That's the first thing we learned, to factor. All right. Now let's look at this one. Find the limit of g of x as x goes to 1, and then this is our function g of x. All right. So this is going to be the limit as x goes to 1 of g of x. Now x is approaching 1. I have a piecewise function. So am I going to use this function, x plus 1, or am I going to use pi? Okay. Would I use pi? Well, no, because it's pi when x is equal to 1. And remember, a limit, x is approaching 1. All right, so we're not at 1. We're getting closer and closer and closer to 1. So we're going to use the one where x is not equal to 1. So that's going to be the limit of x plus 1 as x goes to 1. We're going to use this part of the function. And so then we can plug the 1 in. That's 1 plus 1 is 2. All right. Now let's look at this one. So if we look at this one, let's just plug the 0 in. So 3 plus 0 is 3. 3 squared is 9. 9 minus 9 is 0. Plug the 0 in for h. I get 0 over 0 again. All right. So just like I said earlier, try something else. All right. So let's see what we could do here. Well, I guess I could multiply this out, right? So that would leave me with what? 9 plus 6h plus h squared minus 9 over h. See that? Now, remember, all that is, to get this, that's just 3 plus h times 3 plus h. And then I just fold it out. That's all I did. All right. Now let's see what we get. Well, that's going to be 6h plus h squared over h. The 9's go out. And so, look what I did. How about that? See, got all excited, and I left the limit as h goes to 0 off. So let's squeeze that in there. All right. You got to carry that limit with you. I did that on purpose to point that out. All right, so the limit as h goes to 0. Now in the numerator, I can factor out h. Okay, and then you can see the h's cancel out. And so that's going to be the limit as h goes to 0 of 6 plus h. All right. And now we just plug the 0 in. So that's going to be 6 plus 0 equals 6. All right. See, it's really easy. It's not difficult to do. Okay, it's not difficult to do. All right. So what about this one? Well, let's plug the 0 in. So that's going to be 0 plus 9. Square root of 9 is 3. 3 minus 3 is 0. 0 squared is 0, so I get 0 over 0 again. So let's do something else. Well, you should remember from college algebra or algebra class or pre-calculus class that if you had something like this, you had to rationalize a denominator by multiplying numerator and denominator by the conjugate of the denominator. Okay. Well, in calculus, a lot of times what we'll need to do is rationalize the numerator. So I'm going to rationalize the numerator. So I'm going to multiply numerator and denominator by the conjugate of the numerator. All right, so there we go. So now let's multiply this out. Now, I'm sure y'all know this, but just remember, this is like a minus b times a plus b is a squared minus b squared. So this is our a, the square root of t squared plus 9, and the 3 is our b. And so this is going to be the limit as t goes to 0. Now, a squared, that's just t squared plus 9 minus, and then b squared, 3 squared is 9, over t squared times the square root of t squared plus 9 plus 3. All right, so the 9's cancel out. So that's the limit as t goes to 0 of t squared over t squared times the square root of t squared plus 9 plus 3. And then you can see here the t squareds come out. So that's the limit as t goes to 0 of 1 over the square root of t squared plus 9 plus 3. All right. So now let's plug the 0 in for t. And so that's going to be 1 over the square root of 0 squared plus 9 plus 3. And so this is 3 plus 3. So that's going to give us 1/6. All right. And That's your answer there. All right. All right, so let's look at this. It says, we got a theorem. It says the limit of f of x equals L, or the limit of f of x as x goes to a is equal to L, if and only if the limit from the left and the limit from the right are the same thing. So if we can take the limit as x approaches a from the left and the limit of f of x as x approaches a from the right, if those are the same, then that's your limit. All right. If they're not the same, then what happens? It does not exist. All right. We showed that earlier in this graph up here. Let's see, where is it? That was this right here, where we did that. See, we did the limit as x goes to 1 of g of x. See, they approach two different things, so that limit there did not exist. All right. So let's look at this one. Now, it says prove that the limit of the absolute value of x over x equals 0. Over x as x approaches 0 does not exist. Okay, that's what we want to show. All right, so it does not exist. We got to prove it. All right, well, you know if we plug 0 in, we get 0 over 0. But how do we show it? Well, we've got to show that the limit from the left and the limit from the right does not exist. Now, before we get to that, let's look at this. Remember your absolute value function. Now, you might not have, some of you might have seen this, some of you may not have. Just remember that the absolute value of x is equal to x if x is greater than or equal to 0 and equal to negative x if x is less than 0. All right. So I don't know if you've ever seen absolute value written like this, but this is how you evaluate absolute value. I know in school you've always been told whenever you take the absolute value of a number, it's always positive. That's all you've ever been told. Okay, some of you might have had teachers that showed you this, but if you didn't, this is what you're doing. Okay, so let's just look at this. The absolute value of 5. Okay, let's use this function to evaluate this. So the absolute value of 5. So in this case, you can see x is 5, and 5 is greater than or equal to 0. So that means I'm going to take the 5 and plug it in for x, and that just gives me 5. Well, if I take the absolute value of negative 5, well, remember, this negative 5 here, that is my x. And you can see my x is less than 0, so I've got to plug negative 5 in for x. And so this is going to equal, well, the negative. And then I plug negative 5 in for x, so that's negative 5, and the negative make a positive. Okay, that's what you're doing when you're finding the absolute value of a number. It just always comes out to be 0. Always comes out to be positive. Okay, all right, so now we've got to use this to prove this limit does not exist. All right, so let's go ahead. We've got the limit as x goes to 0, and let's go in from the right of this. Okay, so this is equal to the limit as x goes to 0 from the right. So this is going to be what? The absolute value of x is equal to what? Well, x is positive, right? And what happens when x is positive? It equals x. So that's x over x. So this is the limit as x goes to 0 from the right. X over x is just 1. And remember, whenever you take the limit of a constant, that's going to be that constant. So that equals 1. Now, let's take the limit as x goes to 0 from the left. All right. So this is going to be what? The limit as x goes to 0 from the left. All right. Now, what kind of numbers am I plugging in for x? Well, look, there's 0. If I'm coming in from the left, these numbers over here to the left are negative, right? So this is a negative number in this absolute value. X is a negative number. And if x is a negative number or less than 0, then the absolute value is equal to what? Negative x over x. You see that? And so this is the limit as x goes to 0 from the left, and that's of negative 1. And so this is negative 1. So, all right, so we have the limit as x goes to 0 from the right of absolute value of x over x is equal to 1, which is not equal to negative 1, which is the limit as x goes to 0 from the left. Okay. So the limit as x goes to 0 of the absolute value of x over x does not exist. Well, not really circling that, but that's the proof of it. That's how you prove that that limit does not exist. All right, so now let's look at this. Show that this limit is equal to 0. Okay, so we've got to do the limit from the left, and we've got to do the limit from the right. So we've got the limit as x goes to 0 from the right of absolute value of x. All right. So this is going to be what? The limit as x goes to 0 from the right. And since it's positive, because we're coming in from the right, that is just equal to x. And so this is going to be what? We just plug the 0 in. That's 0. Now, we got the limit as x goes to 0 from the left of absolute value of x, which is equal to the limit as x goes to 0 from the left. And we're plugging in negative. X is negative because we're coming in from the left, so that's negative x. So we plug the 0 in, that's negative 0, which is 0. So we have the limit as x goes to 0 from the right of absolute value of x is equal to 0, which is also equal to the limit as x goes to 0 from the left. So the limit as x goes to 0 of absolute value of x is equal to 0. And that's showing that this limit is equal to 0. All right. All right, so what about this one? All right, so if f of x is equal to the square root of x minus 4, so f of x is the square root of x minus 4 if x is greater than 4, and it's equal to 8 minus 2x if x is less than 4. Determine whether the limit of f of x as x goes to 4 exists. Okay, well, let's see what we've got. So to determine if this exists, we've got to take the limit from the left and the limit from the right and see if they're equal. If they're equal, then it exists. If they're not, it does not exist. So I've got the limit as x goes to 4 from the, let's just go in from the right, of f of x. Okay, so I'm calculating this as x goes to 4 from the right. So that's going to be the limit as x goes to 4 from the right of f of x. Now remember, I'm coming into 4 from the right hand side, so that's values that are greater than 4. Well, what values are greater than 4? That's this first one up here. So that's going to be square root of x minus 4. And so now I can just plug the 4 in. So that's the square root of 4 minus 4, which is the square root of 0, which equals 0. All right, now let's look at this one. The limit as x goes to 4 from the left of f of x. Well, that's going to be the limit as x goes to 4 from the left of f of x. Well, which one am I using? Well, if I'm coming in from the left, that's values that are less than 4. So that would be this second one here. So that's 8 minus 2x. And so I plug the 4 in. That's 8 minus 2 times 4, which is 0. So we've got the limit as x goes to 4 from the right of f of x is equal to 0, which is equal to the limit as x goes to 4 from the left of f of x. So the limit as x goes to 4 of f of x is equal to 0. So this does exist. It's 0. All right. So hopefully all this is making sense. It's really it's not that difficult. Okay. All right. So now we've got the greatest integer function. So the greatest integer function is defined by this. This is the symbol. The largest integer that is less than or equal to x. Okay. All right. So what does that mean? Well, let's just find the greatest integer of some numbers. So if I have, say, the number, say 4.8. Well, what does it say? It's the largest integer that is less than or equal to x. So this is equal to the largest integer that is less than or equal to this 4.8. And you can see that would be 4. Okay. If we did this, if we had 4.1, well, that would be 4 also. Just remember, you're not rounding here. It's not rounding. You've got to go to the largest integer that's less than these numbers in here, or equal to. So if we did the greatest integer of 4, what does it say? The largest integer that is less than or equal to. And so that would be 4 also. Okay, so that's the greatest integer function. So what they're wanting us to do is show that the limit, the greatest integer function of x, as x approaches 3, does not exist. Okay, so for this one, the best way to do this is to sketch the graph and just get it from the graph. Okay, so what do we have to do? We have to take the limit from the left. We have to take the limit from the right. All right. Now, you could just do this in your head without a graph, but let's just go ahead and graph this thing, because I think it'd be good for you to see it graphed anyway. All right, so we've got 1, 2, 3, 4. 1, 2, 3, 4. All right. So let's just start here at 1. So if I plug 1 in, what do I get? If I take my greatest integer function and I plug 1 in, what do I get as an answer? I get 1, right? Well, what if I plug in, say, 1.5? What do I get? I get 1, right? If I plug in 1.99999, what do I get? I get 1, right? It's the largest integer that is less than or equal to whatever that number is. And if it's 1.9999, then that would be 1. Okay, so what this is going to look like is going to just be a straight line across there. But right here when I get to 2, well, if I plug 2 in, what does that do? that jumps up here. So this goes up to 2 but not included, so it's got a hole in the graph. And then they're all going to look like this. Okay? They're all going to look something like that. All right? And then we got this, and then this would go across, and then I'd have a hole there too. All right. So what are we doing? We're trying to show that this does not exist. So let's do the limit as x goes to 3 from the left of the greatest integer function. And let's see what that looks like. And like I said, you could probably do this in your head without drawing the graph. But look, drawing the graph makes it a lot easier. So let's see, 3 is right here. So if I'm coming into 3 from the left-hand side, I'm coming in like this. And so what is it approaching? See how I'm getting closer and closer to 3 from the left? What is the y value? It's 2. All right. And then if I take the limit as x goes to 3 from the right, all right, so if I'm coming in from the right-hand side, well, I'm up here, and it's going here, and then it goes up to here. What's the y value? That's 3. All right. So what do we have? Well, we've got the limit as x goes to 3 from the left is equal to 2, which does not equal 3, which is the limit as x approaches 3 from the right. Okay. So the limit as x goes to 3 of the greatest integer function, that does not exist. And that's showing that it does not exist because we showed that the limit from the left and the right are different. All right. All right, so let's take a look at this. So we've got a couple of theorems here. And the main thing that we're doing here is this squeeze theorem. Okay. But in order for us to use the squeeze theorem, okay, in order for us to do the squeeze theorem, well, we've got to know this theorem here. So if f of x is less than or equal to g of x when x is near a, except possibly at a, okay, so that's saying that when we're close to an x value of a, that the function of f is going to be below the function of g of x. Okay, the function f of x, those y values are going to be less than or equal to the y values of g of x. Okay, and the limits of f and g both exist as x approaches a, then the limit of f of x as x goes to a is less than or equal to the limit of g of x as x approaches a. All right, so if one function is less than or equal to another function, then its limit is also less than or equal to the limit of that other function. And so this is going to lead us to the squeeze theorem. So the squeeze theorem is if f of x is less than or equal to g of x, which is less than or equal to h of x. So in other words, they're saying g of x is in between f of x and g of x. I mean f of x and h of x. When x is near a, except possibly at a, and the limit of f of x and the limit of h of x are both equal to L, then the limit of g of x is equal to L. All right, which, you know, that makes sense, doesn't it? Because see, we can use this theorem here. Okay, so what they're saying is if this is the case, if that's the case, and then the limit of this function and the limit of this function are both equal to L, then the limit of this function has to be L. You see that? That's what they're saying. All right, so let's use that. Let's use the squeeze theorem to evaluate this limit or show that this limit is equal to 0. Okay? All right. So if we did this, okay, if we just looked at this and said, okay, well, the limit as x goes to 0 of x squared times sine of 1 over x. Well, we know that's what the limit as x goes to 0 of x squared times the limit as x goes to 0 of sine of 1 over x, right? Using those limit laws that we learned earlier. That was a long time ago, about what, a little over 45 minutes ago, right? All right. But if we do that and we plug the zeros in, well, this is 0, but this limit does not exist. That would give me 1 over 0 there. All right. And I can't do 0 times does not exist. Okay. So how would we show that? How would we show that this limit is equal to 0? Well, we're going to use the squeeze theorem. All right. So how do we go about doing that? Well, I've got to first, I need to come up with this thing right here. Okay. I got to show that some function is between two other functions. Okay. I need something, I need to start out somewhere. So looking at this function I have here, would you agree that the sine of 1 over x is in between -1 and 1? Does that make sense? Okay, because remember, whenever you're taking the sine of a number, it's going to be between 1 and -1. Because remember, the graph of sine looks like this, right? It's in between 1 and -1. So that's, we know this. That's from trig. Okay, that's from trigonometry. So we know that. So, you know, that's nice having that there in between the -1 and 1. But see, I also have this x squared. Well, I can multiply everything through by x squared, can I? Couldn't I do that? Because and how do I know that I can do that? Well, we know that x squared is positive, so I'm just multiplying the inequality through by a positive number. Remember, if you multiply an inequality through by a negative number, that reverses the inequality symbol. But here we know that we are multiplying through by a positive number. And so this is going to give me -x squared is less than or equal to x squared times sine of 1 over x less than or equal to x squared. All right. So now we're getting somewhere, aren't we? You see that? We're getting somewhere now. All right. So looking at this, if I can show, see, I've got this. Well, if I can show that the limit of f of x and the limit of h of x as x goes to 0, if I can show that those are the same, then that would be the limit of g of x. See that? So I need to find the limit of -x squared and the limit of x squared as x goes to 0. If those are the same, then that'll be the limit of this function as x goes to 0. So we've got the limit as x goes to 0 of -x squared is equal to -0 squared, which is 0. And then we have the limit as x goes to 0 of x squared is equal to 0 squared, which is 0. So you can see that the limit of this function and the limit of this function as x goes to 0, those are the same. All right, you see that? All right. So we've got the limit as x goes to 0 of -x squared is equal to 0 which is equal to the limit as x goes to 0 of x squared. So by the squeeze theorem, the limit as x goes to 0 of x squared times sine of 1 over x is equal to 0. And so there we have shown that this limit here is equal to 0. And that is all of this video. So just to recap a little bit, just remember, whenever you're evaluating limits, plug the number in, okay? Plug the number in. If you get 0 over 0, try something else. So what did we do when we tried something else? Well, we factored and canceled out a common factor. We multiplied by the conjugate. We rationalized the numerator. And then in that one, we just kind of multiplied the numerator out. And if I can get back up to it, this one. See, we just multiplied this out, combined like terms, and see the h is canceled out. So that's some techniques that you've learned. And then just remember, whenever you're doing the limits of absolute value, okay, you've got to see inside that absolute value, is it positive or negative? Okay, don't forget about this right here. Okay, and then remember, you may have to show that the limit from the left and the limit from the right are the same in order for that limit to exist. And if they're not the same, then that means the limit does not exist. Okay, so the way that you can get better at this and get pretty good at it is just practice. You're gonna have to work problems. Okay, and look, I've got some other videos just like on specific things. If you check my YouTube channel, the playlist that says limits, there's a bunch in there on limits and stuff. So check that out. Hope the video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching.